Welcome, everybody. Thanks for joining. This is Jeff Crozier. I think I know most everyone here, maybe not all, though. So anyway, I'm in Orange County for the most part, and I am your guest presenter today. This presentation was put together. I think it was put together for a class for some mostly non-technical people. So a little bit of it will be pretty basic, and some of it will be a little bit more interesting, depending on our audience. So this is an introduction to seismic retrofit of reinforced concrete and masonry structures. This is part one, although I think the invite said part two. We had to cancel, we pushed back part one a couple times. Part two will be presented in a couple weeks, and we'll see who's presenting that. Anyway, today we'll kind of go over some of the basics of seismic retrofit, why, what, how, and then we'll cover the reinforced concrete section. Then next week, well, 2 weeks from now will be the masonry piece. So here's the class outline. What is seismic retrofit? Guidelines, common deficiencies, and then options for existing buildings. So that's kind of what we're going to talk about. Obviously, most of you engineers well know that seismic retrofit is, basically it's an improvement of an older existing building, either one that was either designed when seismic engineering had not evolved to the state it has as of now, or even the seismology, on the ground shaking was not as well known. So, usually the goal of that is to make a building better, either serve a different function or serve a new function. Or just be a better investment for the owner of the building that wants to reduce their risk. Again, what is seismic retrofit? It's basically removing vulnerabilities and increasing the overall resilience of the building. Really, we look at two types: conventional, which is basically using more improved analysis techniques and using the same materials that may or may not already be in the building. Either strengthening concrete, masonry, or even steel. And then there's some, what Miyamoto is really famous for, what we're really, really good at is doing, more advanced techniques with stuff like FRP, fiber reinforced polymers, fluid viscous dampers to damp the building's motion. Buckling restrained brace frames, which are BRBs, we use a lot of those, and or base isolation. So those are kind of some of the things that we really do well versus other more conventional engineers. So we'll get to some of those things as we get into the presentation. There are many codes and guidelines for retrofit of existing buildings. The IEBC, International Existing Building Code, is more of a national document that's used around the world. ASCE 4117 is the current version of the seismic evaluation and retrofit of existing buildings. We use that very, very heavily. It's kind of the basis of a lot of work we do. And also 2019 California Existing Building Code, which is part 10 of the California Building Code. That's really essentially adopts, the IEBC and puts a little bit of a California spin on it. And you'll find the DSA and OSHPD provisions in there, which are a little bit special, a little bit more unique. ASC 41 really is the universal standard for both for evaluation and retrofit of existing buildings. There used to be two versions. There was an evaluation document, and then there was the seismic improvement piece, and they've since combined it into one document. But that's kind of the backbone of a lot of the work that we do for assessment. It does have a three-tiered approach for doing the assessments, and we'll talk about that in an upcoming slide. It also has targeted performance levels, and it also contains, seismic hazard levels. You can pick your seismic hazard level, either from anywhere from a maximum credible earthquake to some kind of reduced design-based earthquake, and you can hit different performance objectives along the way. So it's a pretty useful and what do I say, adaptable tool to use for different buildings and different goals based on the owner's or jurisdiction's requirements. It does sort out deficiencies, so we'll talk about that a little bit in coming slides. as I said, establishes analysis procedures and acceptance criteria. There are 3 tiers, as we mentioned before. Tier 1 is really, it's really just a screening. It's a rapid pseudo engineering evaluation of a building. And really the tier 1 screening is really, it targets things that we know work well just by experience and, by past performance. And it kind of lets us move beyond those. And then it clumps other things that we're not really sure about into, it'll classify them as deficiencies when they may or may not be deficiencies at that point, because tier 1 is it's very conservative and it's very broad. So it's really identified stuff that we know works well and just don't worry about that. Tier 2 is really a deficiency only analysis and assessment. After we've done our tier 1, it'll allow us to much more deeply evaluate the characteristics of a building that didn't pass the tier 1 screening. And then tier 3 is really it's a full building analysis. It can be lead to design of either the full building or full building with new elements and new features put in. So there's my ASC 41 lesson. So what do we need to do an ASC 41 building? Well, evaluation. Typically, we like to get all the as-built documents that are available. Typically, structural drawings are extremely valuable, particularly for concrete or masonry buildings, because we can't see the reinforcing when we go to the site. We like to get everything we can. Structural, architectural, MEP, anything that has an impact on the buildings. And then try to understand what the lateral system is and the lateral elements. If we don't have drawings available, then we kind of have to create as-builts from trips to the building, documenting everything we can, or even engaging a testing lab to create as-builts from some doing non-destructive or even destructive testing as needed. Usually if we cry, that costs us a lot of time and a lot of money. Usually I find if we cry that we need to do that and here's how much it's going to cost to do that, suddenly the drawings appear. So don't be afraid to try to find that information, because it's incredibly valuable, as you know. As I said, for reinforced concrete structures, creating as-built is quite the challenge. A lot of times we'll have to do some kind of investigation to determine what the actual rebar is, the spacing, the size, everything, associated with the building. And a lot of times that's very difficult to do. Or very expensive, X-ray and stuff. And, even there's a point about foundations. It's hard to dig up the whole foundation to see how big the footings really are, or if they're deep foundations, what they are and how deep they extend, because it's almost impossible. As I said, site visit, we always want to visit the site if we're doing an evaluation, even if we have the drawings, because if it's an older building, one, we want to ascertain that there haven't been, modifications made to the building, large additions that we don't have any documentation on or anything of that sort. Or if they haven't, cut big holes in the shear walls, if it's a shear wall building, or they hadn't made, wholesale structural modifications of the building. So it's always important to document that. And a lot of times it's also valuable in that last bullet point to get a geotechnical engineer involved, just so we understand either one, the site's seismology, the soil type, and two, if we're going to have to design new foundation elements, we want to look at those with the perspective of, we're evaluating an existing building that's been there for a number of years, and maybe not looking at design parameters based on a new building that's going to have a lot of settlement, at initial construction. So there's a lot of things to think about when doing seismic evaluation. Common deficiencies. Well, this just kind of goes back to all of you. I mean, for reinforced concrete, everything really goes down to non-ductility or lack of ductility. A lot of it goes back to the older methodologies used to analyze buildings, where we didn't have the sophisticated computer software that we have now, and people were doing stuff with presumed assumptions and slide rules or even hand calculators. And we'll talk about Olive View Hospital a little bit. And the VA Center was a good one. Olive View was a soft story and non-ductile concrete, and it just performed miserably. It wasn't a very old building either. I forget the year it was built, but in the 71 San Fernando earthquake, it essentially collapsed. the first story pancaked. It was a very tall first story, which is pretty common. In a lot of the buildings we do, the public spaces on the first floor are always, they take more volume, they take more of this, they take more of that. And a lot of times the buildings are taller in the first story than they are in the uppers, which creates a more flexible story. So with the more flexibility, generally becomes a softness, or if it's not carefully designed for or well known, which it wasn't at the time of this building, and also the ductility in the columns wasn't adequate to allow that to stand. I mean, this one event created Oshpod as the structural reviewer for all hospital projects going forward. So everything post Silmar, which really came into play, I think, in the '73 building code, Oshpod had jurisdiction over all hospital projects due to this collapse. It was actually a terrible event. I think 60 people died in this building, and they couldn't evacuate people, and it's just kind of a wreck. Non-ductile concretes, they are brittle, they aren't ductile, they don't have a lot of post-yield capacity, and they don't have the ability to dissipate energy over a longer shaking event. So that's why they're of massive concern. And with brittle failures comes rapid collapse. So that's one of the things we're very attentive to as we do our engineering work. As it says, prior to '77, really prior to '73 code, there was a lot of non-ductility allowed in the building code. So, that's the tools the engineer had. So that's what we used. Common deficiencies really are lack of ductile detailing in the columns, or even walls for that point. Not enough transverse reinforcement to keep the concrete and the core confined and keep them very, very ductile. Typically we won't do anything in columns with ties more than 4 inches on center, and for frames sometimes even closer and larger bars. So, and also the older stuff didn't have, and we see this around the world today. They have 90-degree hooks, at the where they terminate the ties instead of the 135s that bend back. And we should have had a picture of this. It's not in here, but the 135s bend back into the core, and they at least keep the vertical bars in place. They keep the concrete in place, so the reinforcing can yield and the concrete will still be there. Here's some stuff from Indonesia, Mexico City. We saw a lot of maybe even worse stuff in Haiti, where the typical Haiti column of old was 4 small bars and number 2 pencil rod ties at about 12 inches on center. So very, very, very little confinement and very little ductility. So the soft story, as we talked about before, where the ground floor really is taller, and that's basically a building function and use, thing. And we see that in a lot of buildings we do. The displacement at the ground floor can be very large if it's not properly accounted for or built into our models. And we can get hinging, we can get a lot of drift in the first floor, which is different if you have a very stiff building above that. So it creates a not only soft but a weak story. So, and as I said, hinges at the ground floor levels. So this looks like a stick frame building. This is the Marina District in San Francisco. If you remember Loma Prieta, if you're that old and we're around there, a lot of the residential buildings, they had horrible soil in the Marina District. It was a lot of bay mud infill. I think it was probably land recaptured. And of course, all these residential buildings, they had garages, on the first level. So, tons and tons of openings, and then, relatively stiff boxes on top of that. So, they're very soft at the first level and very stiff above that. So that's an irregularity that just causes a lot of damage. So a lot of these buildings collapsed. It was interesting. I remember at the time, whatever direction the earthquake hit, if all the garage doors were open, then the buildings fared very poorly. If the garage doors were shut, they tended to do a little bit better because the garage door could act somewhat as a strut and tie to keep to resist some of the seismic forces, which is kind of a small thing, but it was definitely noticeable. Some of the other things that were interesting, you'll see in older buildings, smooth bars. We used to see the twisted rebar. That probably went out of play in about the 30s or 40s. Now we use nothing but deformed bars, so they anchor and they bond with a concrete a little bit better and a little more capacity. A lot of inadequate lap lengths where we splice bars together. The older provisions were really very, very poor as far as lap length requirements. And usually if we evaluate an older building, we'll see that kind of issue pop up somewhere or other. And then we have, different things we can do to treat that. And not enough longitudinal steel to resist the bending moments in the building. And then also, again and again and again, inadequate transverse reinforcing to confine the longitudinal reinforcing and keep the concrete in place. Concrete shear walls, well, a lot of times they behave like columns, where you have large compression forces, at the ends of the walls as they try to overturn due to the earthquake forces. And then the other thing we're pointing out here is lack of shear capacity. And obviously we want, in shear walls, we want them to be bending controlled so that they're more ductile, so that the wall will yield before it fails in shear. Because a shear failure is usually a lot more, it's a lot more brittle, or it's a lot more catastrophic. A ductile yielding of the boundary elements of a concrete shear wall is actually a pretty predictable thing to happen. And that's where we want to drive our designs today. They didn't have that knowledge back in the, when we're doing a lot of concrete buildings in the West Coast, the 40s and 50s after the war, there's a lot of non-ductile concrete buildings built, without the advanced engineering capabilities that we have now. And I said inadequate compression force at the base. I think we got a picture, yeah. So you can see the end of this wall where the bars have buckled out, and there's a good amount of bars there, but they're not very well confined. If that had had a lot more ties like we would have today, that probably would have fared a lot better. It would certainly be cracked, but it's still serviceable and it still has strength and it can still resist load. As it is right now, it looks like it looks like a bending failure. We're saying shear, but it doesn't really look like shear to me. But that's not a good wall anymore, and it doesn't have any capacity. A lot of things we see are really just incomplete load paths, or a lot of things not thought out about how the building works comprehensively. No collector elements to bring the load to the lateral force resisting elements, or inadequate collector elements or cords or that sort of thing. A lot of times the connections from the diaphragms to the walls or the lateral elements are inadequate. And then the same thing with the walls to the foundation. In Northridge, I saw a bunch of wall shear failures at the bases where the shear walls just slid off of foundations. Well, they didn't slide off, but they moved several inches and they fractured all the bars, and it was a really interesting study. And then any discontinuous lateral force elements, kind of the regularities. I think, and we'll show some of that stuff in a later slide, but this sort of stuff where you have a shear wall in the upper, if you can see my cursor on the upper level that's offset from the lower level, that needs to be dealt with very carefully because there's large forces that need to be transferred, and they really need to be transferred. Now we designed all these things at what we call a mega level load, which is really it's the full earthquake response level load. Whereas for the rest of our building, we design, on reduced loads, thinking, presuming or knowing that there's a certain amount of ductility. Well, with these sort of elements, we take out some of the reliance on ductility, that they will behave well. And, as we look around the world, I know a lot of us spent a lot of time in Haiti, and we looked at a lot of different buildings. And, one day I was wondering, I'm wondering, why didn't every building collapse? Because they're essentially non-engineered for the most part. And, we saw a lot of collapse and very well damaged buildings, but we also saw a lot of buildings that really had little or no damage. And sometimes that was amazing to me. But the one feature that really led to observation of a lot more damage was a lot of irregularities. we looked at a lot of just big warehouse buildings. I think they're all like 30,000 square feet, pretty much 100 by 300. And it seems the ones that had like little 2-story offices in one corner that were made out of block or masonry, those had little hard spots in them, and those tend to just tear themselves apart. And a lot of those collapse, whereas ones that had none of that, it was just a big open box. They tend to fare very well, and which was shocking because you wonder how could they stand up at all, because they're, they probably shouldn't have, but somehow they did because they didn't have the irregularities. So I think that points out how much stress concentration could be caused by these little irregularities is the load tries to move, from one part of the building to the other, and they tend to respond, less predictable, I think, than our analysis shows, or at least our analysis at the time. So here's some of the options, we can use to provide more ductility. This is a concrete column that was found to be not very ductile. So one of the solutions obviously is to put more reinforcing in it. We jacket it with a bunch of new rebar and a lot of confining ties. You can see these ties they're probably number 4s, maybe number 5s. I can't tell how big this picture is, but they're about 3 or 4 inches on center. So that's a pretty good amount of confinement. And they're also doweled into the existing concrete column. So that's one of the methods you can do to provide more ductility. And another thing it says, well, there'll be other elements too, either addressing the walls or the frames. FRP, fiber reinforced polymers, is another way as well. Instead of adding ties, we can wrap columns with this, and this provides an immense amount of ductility without creating a bigger volume. And it's actually relatively easy to install. But a lot of times we'll have to do a little bit of stuff to the columns. I think you can see if you look carefully, these corners, they've been rounded so that there's no real hard points, so that the FRP has a little bit of ability to provide some tensile capacity surrounding the column. But this works pretty well, and it's fairly easy to do. And if you have a situation where you don't have volume that you can take up with more concrete, this is a really good solution. Soft story, we've certainly done a lot of these. West Sacramento office is probably the leader in the world in doing, interesting seismic retrofit projects. This one, it shows we're putting a BRB, a buckling restraint brace frame, bay into a building, and these things work really, really well, and they're very ductile. And they're also pretty predictable. So they do a really good job of controlling story drifts and, protecting the rest of the building and the other elements that are in place already. And as we point out here, drawback is that increased stiffness results in increased lateral loads, right? Because we all know that if our buildings become stiffer, they react more violently to earthquake forces. A nice soft response is great if we can control the deflections, but sometimes there has to be a balance of the two. Here's a really interesting soft story retrofit we did. I think this is 555 Cat in Sacramento. It's right downtown. Amir and the corporate team, and I want to say Lon and Bob worked on this. Probably, I could be wrong. I'm probably giving credit where it's not due, or vice versa. But we did a ton of analysis on this building. It's probably it's a big building. It's I don't know how many stories it is. I'm gonna guess it's 15 or 20 or maybe more, all concrete. And it had a tall first story, and it had a soft story issue. And we're able to resolve the soft story and really all the rest of the building issues just by putting in some fluid viscous dampers, which you can see here in the picture. This is right in the middle of a coffee shop, and they don't look bad to me. In fact, I like them a lot. But they, they act like big shock absorbers. So they don't add stiffness to the building. What they do is they really work out of phase with the building's motion. So the dampers are working very hard when the building is back at its original neutral position because it has some velocity. So when it's moving back and forth, and it's at its at rest position, the damper has been activated, and so it just dissipates energy by moving, viscous fluid through from one chamber to the next, and it kind of kills the energy like a shock absorber on your car. They work really, really well, and they're very high tech. And one of the benefits to this, it doesn't really stiffen the building. It just adds damping. So a lot of times we can avoid a lot of other work, in the building to fight the stiffness, gain. We don't have to do a lot of foundation work typically, and we don't have to do a lot of cord and collector and a lot of other stuff that, if we don't have to do it and we don't have to spend the money, and we can do it using the dampers to dissipate the earthquake energy rather than the building frame, that's usually a very nice win. So we like this technology a lot. I think Miyamoto is probably the world leader in doing fluid viscous damper work. Yeah, like I said, this is kind of all the stuff I just said. So this was a very, very flexible building, but now it's a lot better. Some of the other things, if they're frames or even beams and column stuff, obviously this is kind of like the column we saw before. We can add concrete, we can add reinforcing, and the challenge is just getting the detailing right to make this constructible and actually make it work. But it's certainly a method. We're basically designing something that, if we were designing it now, we probably would have had all this stuff in there anyway. The beams and the columns would have been bigger, and we had more reinforcing and provide a lot more ductility. I'm kind of surprised in this picture. I'm not sure where this is. I'm kind of surprised there isn't more column ties there, but maybe that's just me. I like lots of column ties, so your columns are very ductile and they can handle whatever deformations come their way. Another thing we can use with FRP is to add strength to beams and slabs and other elements, because FRP can really behave like tension reinforcing, only it's applied externally. It's not internal to the concrete like rebar is. So this can work very well. We can also add confinement and add shear strength to concrete beams, and concrete columns as well. You can see this one, they've kind of wrapped a beam, and you can't quite see it in the picture, but there's these little anchors that anchor up into the slab. And we've done that on a number of jobs, and it tends to work pretty well. It's been tested quite extensively, and it's a very good solution. So something to put in your little toolkit. And here's kind of what it looks like a little bit as we're going. So yeah. And again, here's the FRP. Can't really see. There's not really a good picture of those anchors dialing into the slab of the FRP. It's kind of pretty cool, actually. But you wrap the top and the bottom, it adds a lot of shear strength, and it also adds confinement. So it's a very good technology. I like it a lot, especially when you don't have headroom issues. This looks like a parking structure beam to me. I could be wrong, but it looks like it's shaped like one. So, and then how to strengthen shear walls. I mean, this is the what I like to call the good old dumb brute force methodology, where our wall doesn't have enough strength, so we just provide more wall. We dial into the existing wall. We add a bunch of reinforcing, and then we shotcrete it, to strengthen and stiffen the wall. This actually works very well. It's simple to do. We've got a few projects going on right now where we're doing this, and it's just not very sophisticated, but certainly worthy of doing. It's usually the cheap and easy way to do it. And if you have a shear wall building, it's you already have a stiffness, so it never seems to hurt to add a little bit more strength. So. And like I said, it's easy to apply. There's a lot of good shotcreters out there, and it's pretty simple technology. We just gotta do a good job of engineering the new walls, and that's pretty easy. And here's another method too, with adding shear strength in with FRP. And it looks like there's also some boundary improvements at the end of the wall too. With you can see the vertical FRP at the ends of the walls, and then the horizontal strips of shear reinforcing that's been added to this wall to strengthen it. Like I said, this is pretty easy to install too. So I mean, a crew can come in here and it's essentially they're just gluing fiberglass or some kind of more exotic material. Usually it's glass because that's cheaper, and then the carbon fibers, and even Kevlar is available, but that's you kind of go up the scale, they become more and more expensive. So if you can do it with the less expensive materials, it's usually pretty easy to do. Again, another picture of a confined end of a concrete shear wall. Looks like we're improving we're increasing the shear wall. We're adding a boundary element to the end of the shear wall. So again, it's just adding concrete, and it's adding a lot of reinforcing and a lot of ties that create ductility. So pretty interesting. We'll be doing a lot of this after the next good size earthquake, all of it. And again, here's a diagrammatic of a, kind of a boundary element of a FRP, the shear wall. As you can kind of see these little, I don't know if you can see my cursor, but these little things that look like fantails, they'll run those through the slab and they'll anchor them to the slab below. So those are what creates the continuity in the FRP from one level to the other, and it works really, really well, surprisingly. And we've done that. Like I said, we've done that in a bunch of projects. I think Wayne and Pete and John Buckley did it at the CSI building in San Diego.
Hey, Jeff, this is Pete.
Yes, sir.
I don't know if we can do that for flexure. And I don't know if Wayne's and if he can chime in, but ours was basically meet prescriptive requirements for some city of San Diego not knowing how to use ASC 41, but I thought we could only use it for shear, not for flexure, because it's not ductile or it's force controlled, and you have to look at it differently.
Yeah, I'm sure there's different provisions in different jurisdictions, but at some level, it probably is. I don't know.
Yeah, you're going to get some ductility from you're not going to get any ductility out of the fiber wrap itself, but from the connection between the concrete and the FRP, like the glue, you're going to get debonding there, and that's where you get some of your ductility. It's not going to be nearly as good as like a piece of steel would, though.
Yep. Yep, there are many tools, is all I'm going to say. But these are options. Yep. So check with your local jurisdiction and all your local requirements. Again, here's an added boundary-like element, at the end of a concrete shear wall. We've got a lot of pictures of these, but it's kind of the same idea. Add bending capacity to the wall and add confinement to make sure it behaves as we intend it to. Yeah. Again, more concrete shear walls with FRP. This says it's providing confinement for compression. Could well be if it's properly anchored and detailed. And again, the benefit is it doesn't really take up space, or it doesn't take up much space. So that's sometimes that's a make it or break it deal to your project. So be aware of that. The incomplete load path thing, this is kind of demonstrating a picture of a drag element that's been placed in a building where the slab or there was an adequate rebar in the slab to provide drag forces to tie it into a new shear wall element, or maybe even an existing shear wall element where the building would be weak in the diaphragm. So this is kind of a good method that's relatively simplistic. Just adding concrete, adding rebar, and adding ties to drag that element along. Not hard to do, but as this last bullet point says, you're always going to conflict with existing pipes and ducts and who knows what else. So, those are things that'll have to be coordinated, or if you're going to do something like this, make sure you kind of, expect a coordination process to get this stuff into the building, because there's always competition for space in these in the interstitial spaces of an office building or any type of building, really, because it's just loaded with stuff for the most part. And here's another diagram. We're adding tension tie capacity or drag capacity to the top of a slab using FRP. And this is certainly viable as well, because it can add as external reinforcing, just like we would, but internal reinforcing in our concrete slab. If we're doing this in a new slab, we just put more bars in, and we maybe put ties around the bars if the forces are high enough. But yeah, this is something that can easily be done, and it can be done either on the top or the bottom. Very easy to put it on the top if you have the space, and you have a flooring that goes over it. And here's kind of a shear transfer detail. This seems to come up a lot if you have inadequate slab bars that are tying your slab to your concrete shear walls. So this is a way to improve that. You can add FRP to transfer the shear from the slab to the wall. So that's a pretty, I don't know that we've done this, but I know we've done more brute force, dumber things like, I don't want to say dumber, but the simplistic stuff where we'll add some kind of bent plate that bolts to both the slab and the wall. And I kind of question how well that really works, just from a compatibility basis. But we can certainly calc out the numbers, and it certainly provides some strength by doing that. So, if that's our best hope, that's what we should do. But these are, which is what we talk about here, conventional steel angle below slab, post installed, blah, blah, blah. I think the FRP is probably more compatible with the concrete, maybe the steel and the expansion anchors. That's my opinion. It's not based on any fact. So, and I don't have any research to back it up. That's just my thought as 35 years in engineering. Again, here's the angle sort of approach, or dowels. So there's lots of options to solve these problems, but these are problems we'll see again and again and again. I know Veronica and I were looking at a report that I want to say somebody did. It was up in Reno at it was at a healthcare facility. Oh, Renown. They had somebody do a report, and they had an existing concrete. I think it was a CUP, Central Utility Plant, and the building had a bunch of issues, but the engineer only suggested that they do this. And we started asking questions, and they went back and, well, yeah, there's probably really a lot more things we need to look at. So it's kind of a flag that this would seem like the last thing you'd look at. And for some reason the engineer didn't really look at things very comprehensively, but they came up with a nice slab to shear wall, improvement detail in their report. So it was kind of interesting. Oops. So there's that. Again, here's the thing with FRP. Here's the FRP anchors. So this anchors the vertical FRP. So that's actually a better picture. That's kind of what they look like too, as they pass through the slab and they anchor in top and bottom with the fantail looking things. So there you go. Yeah, discontinuous lateral load pass. This is always a big exciting point for us, because in older buildings they just didn't really treat this very well. They didn't really have the knowledge that we do now. Obviously, if you have this sort of situation, you can stick a shear wall under the one on the right that's quite irregular, and that'll solve a lot of the problems in response. Yeah. Another solution, add BRBs or fluid viscous dampers to a situation like this. This must be a situation where that shear wall on the upper level must transfer to another line somewhere else in the building. In addition of something like this would keep it would certainly control the deformations in this line, and the dampers would certainly add damping. So that's never really a bad thing. And also there's large overturning forces generated by this kind of configuration that, it says verify column strength in below ends of shear wall. So that's always a concern that probably wasn't adequately dealt with, way back when, because at the onset of seismic design, we would not, I was not gonna say we, because I wasn't doing it, but This is well before my time. They would just design the building for 10% of its weight as a lateral load. And, you know, it was all working stress. So there wasn't really an expectation of any ductility. That wasn't well understood, or wasn't understood at all, but it was, you know, that was the first step. You know, now we've taken a lot of steps and we're getting pretty good at this. And we still have ways to go, I'm sure. I'd be interested to see what we're doing in 40 years and look back at the stuff we're doing now and go, I wonder if we'll think we're a bunch of idiots. Probably not, but there will be some of that for sure. Anyway, that is the end of part 1.